So basically we will continue with Gaussian elimination. We started last time. So what did we mention that Gaussian elimination is? Last time we solved the problem, 2 by 2 system. It was a very small system. And it was a procedure that I used that is actually named Gaussian elimination. The procedure that we used last time to solve that 2 by 2 problem is called Gaussian elimination. Okay? So particularly what is specific now in a 2 by 2 problem, you've learned that in your high school math probably how to solve a system of 2 equations. And that you can basically use various ways to do it. But here we're actually looking for a systematic way that we can actually program. So 2 by 2 systems, it's easy for you, that is a human, look at the problem and just figure out what would be the quickest way to solve it. Maybe you will express x2 in terms of x1, plug it into the number 2 equation. Maybe you will figure out how to add the 2 equations to eliminate one of the variables. There's a number of things you can do just by looking at the problem. But we actually need a systematic sort of algorithmic way for solution that we can actually program. And we will, by the end of this program, a problem. So that problem, or that algorithm, was first identified by Gauss, a 19th century mathematician way ahead of his time. So let's actually, so this is basically a solution procedure for systems of linear equations. In the first step, we actually take the system that we have and we manipulate the equations in the system to actually get it to the upper triangular form. Upper triangular form means that when I look at the matrix of coefficients of the system, it's upper triangular, it has zeros in the lower triangle of the matrix. So first step is get the system to upper triangular form. And second part is then use the back solution, the basic back substitution to solve the problem. So the last equation will be very simple. It will involve only one variable, so I can solve it and I can then keep plugging that solution in to my equations above that. So use back substitution. To solve the system. So let's actually have an example. Look at the example. This is going to be a little larger example, 3 by 3, to solve that. Minus 3x1 plus 2x2 minus x3 is equal to minus 1. 6x1 minus 6x2 plus 7x3 is equal to minus 7. 3x1 minus 4x2 plus 4x3 is equal to minus 6. This is my system. So let me actually get the, do I have the list of names? I don't have the list of names, so I'm just gonna go and start up there in the upper right corner, which is upper right corner for me. So what would be the matrix of coefficients for this system?
Are you including the solutions?
You mean right hand side?
Yeah, so it'd
Yes.
be negative 3, across the top negative 3, 2, negative 1. And then you draw a line.
Mm-hmm.
And then it'd be negative 1 again.
Okay.
And then you do 6, negative 6, 7, negative 7, 3, negative 4, 4.
Alrighty. So next to you, so how do I call this matrix? We had an name for it last time. These are my coefficients from the left-hand side, right?
Yeah.
And we call that A.
Yeah.
And these are my right-hand side, which is B. And this whole thing together is called augmented matrix. Okay? So basically, I'm augmenting my left-hand side coefficients with the right-hand side. So I sort of have A and B, and the system I'm solving is AX is equal to B. Okay? So I'm looking for X's. So what does it mean for this system to get to upper triangular form? What would I like for some of these coefficients to be, and which ones?
1, 6, 3, negative 4 to be 0.
Did I ask you? So what would I like to coefficients to be? Thank you.
Yeah, 6, 3, negative 4 to 0, and
I would like them to be. So what I said is like I want to get the system to upper triangular form. So this matrix should be upper triangular, okay? Which means that these three should be 0. Okay? Now I could go with the lower triangular too. Would work pretty much the same way. But this is just the system that is in. So I want to get this 6, this 3, this -4 to be 0. And now basically that's what we're going to get. So next to you, if I actually, I'm just going down the row up there. So if I label these rows with like Roman numerals, what transformation or what could I replace my second row with? There's a linear combination of these rows that would basically get this 6 to be a 0. Can you come up with a
2 times row
2
1.
times row 1, and I add it to,
Row 2.
yeah. So basically I'm gonna replace this by 2 times row 1 plus row 2. So I'm gonna have 2 times -3, which is -6 plus 6, that's gonna be a 0, okay? And we know that I can always, like when I have the system, I can always replace one of the equations with a linear combination of the others, okay? So that doesn't really change my solution. So that's what we are gonna do. So we're gonna replace, so first row I'm just gonna leave as is. Okay? So -2, so next person in line. Can somebody help me with this in the upper row?
What?
Yeah. Can you help me? What is this?
0, -2, 5, -9.
Person next to you, is that correct?
Yes.
Did you really check?
Yeah.
All right. All right.
It's all about trust.
So next one. So what am I going to do with this third row?
Me?
Yes.
Row 1 plus row 3.
That works. Okay. So when I do that, what am I going to get?
0, -2, 3, and -7.
All right. Okay. So I eliminated my coefficients in the first column. I made 0 those that I want to do. Now actually proceed, but I'm going to now start from this position and use this second row to do something about this. Now it's -2, it used to be -4. I would like this to be 0 as well. So basically so these are the positions on the first go, and this is now position on the second that I want to eliminate. So what would work in this case?
Multiply the second row by -1 and then add them.
So basically it's first minus second, right? Same thing. So there's no,
Third minus second.
what works here is second minus first. What works here, first minus second.
Is it third or third?
Second and third. Yes, good job. And I don't want to work with the first row anymore, because if I do anything with the first row and I add it to the third, I'm going to have something non-zero, so I'm going to mess up this coefficient here. I don't want to do that. Okay? I want to work with the second row, because second row has 0 in this position 2, 1, so that's not going to change my position 3, 1. So these will remain intact. So I don't want to keep doing this forever, right? So I got to actually do systematically. So let's do that. Can you help me add these two? I'm actually, yeah, I'm gonna have to say control, save. Just a second, I gotta go to the page 2. Okay, so I would like now, so what is it going to become?
Third row will become same as third. So 0, 2, negative 16.
A negative, are you sure?
0, 0, 2, negative 16. Sorry. Apparently I'm wrong, but
So it's gonna be -9 minus -7, which is
negative 2.
-2. All right, so let me just see what happened with my pen here.
Dr. B, I'm not sure that's right.
Okay,
I think on the last page, you
I'm actually not seeing my first page anymore, so I'm completely trusting here.
so -2 and then 2.
So I have 0, 0, -2, and then 2. All right, and I'm just gonna,
So we're doing 3 minus 2, not 2
Yes,
minus 2.
it's 3 minus 2, the last page.
Okay.
okay, so that's 3 minus 2. Not 2 minus 3, either would work. So whichever one you want, I can do. 2 minus 3, or what did I write on the previous page?
You accidentally wrote 2 minus 3, but it should have been 3 minus 2. That works.
Works just fine. So which one is this? I'm not looking at the previous system, so. Is this 2 minus 3 or 3 minus 2?
2 minus 3, but it's going to be different than 3 minus 2.
So this is 2 minus 3?
Sure.
That works.
Yeah, that's 3 minus 2.
All right. 3 minus 2. Okay? So point here is, while solving by hand, okay, it all works. So there is multiple options. Which one we choose when solving by hand, it doesn't matter. And let me actually now go in through my papers and look at, okay, so what was the other ones were -2, 5, -9, -3, 2, -1, -1. Okay. So basically this is now my upper triangular system, okay? So this is step 1 is finished, so I can actually start solving the system. So this system, for instance, this last equation, what it's really equivalent to in terms of a linear equation is -2 times x3 is equal to 2, right? So basically I can do step 2 back substitution. So this third equation is -2 x3 is equal to 2. Does everybody see how is that the case? Okay. I treat this as a matrix A, so that matrix A multiplies a vector of unknowns x1, x2, x3. Okay. So when I multiply in the last row, I'm going to have -2 x3 is equal to the right-hand side, which is 2. So my x3 is obviously -1. And I can plug that into my second equation. So could you plug that in for me? And
I got
So it's minus 2x2 plus 5 times minus 1 is equal to minus 9. Minus 2x2 is equal then? So x2 is 2. Okay? And then next person in the second row up, Nick, is it?
Sorry, you want me negative 3x1 to 3?
Yes, so it's my first equation is minus 3x1 plus 2 times 2 minus 1 times minus 1 is equal to minus 1.
And you get x1 is equal to 2.
So this is equal to minus 6, you say? Indeed. So this is my solution to the system. Okay? So let's actually now, so this is actually basically the system solved. Now let's actually see for a moment if we can actually figure out some rules that we could actually try to program later on. So I just want to actually come up with some rules. Open 3. So if I had some general system, and this general system was in the form A11, A12, A13, and B1 on the other side, and then I have A21, A22, A23, and A31, A32, A33, and B3. So if I had like a very general system, I'm now trying to identify some rules. What should I replace my second equation with? Let's say, and let me make it more specific. Let's say that I want to replace this with equation 2 minus some coefficient c times equation 1 in order to make this position 0. What should c be? So essentially my A21 minus c times A11 should be 0, correct? Is everybody following what I'm doing? In order to make that position 0, I want this entire row minus some coefficient times the first row that will make that position 0. That means that in the first position I'm going to have A21 minus this coefficient c times A11 is a 0, which makes c, the choice for the coefficient, be what? Yeah. So basically this should be 2 minus A21 divided by A11 times 1. So by the same logic, what should I replace this row with? It's again some coefficient c. What should this coefficient be? And if I had more equations, I would just keep going, right? Until I'm done with all of the rows. So, okay, let's say that I do that. So then I actually have A11, A12, A13, B1. And I had a 0 here. I just have here now a new coefficient that I don't want to calculate what it is. I'm just going to call it A22 tilde, A23 tilde, B2 tilde, and 0, A32 tilde, A33 tilde, B3 tilde. And then I would replace this with what? row 3 now, minus which coefficient times 2? C, and this C satisfies that A3 2 tilde minus C times A2 2 tilde is a 0, because I want this to become 0. So what is C? Okay. And if I had more rows, I would just keep going. This would become A4 2 tilde over A2 2 tilde, A5 2 tilde over it, and I would just keep going as many rows I had. Okay. Do we see similarities? Could you actually see yourself programming this using a for loop? I start, if I'm starting from the first position in the for loop, I keep going with all of the rows below that first one, right? If my so-called pivoting position is A11, okay, I do a for loop on all of the rows below, however many I have, and I do that operation. Then I move on to the second pivoting position, which is A22, and I do the similar operations on all of the rows below, and so forth. Okay? So those are actually two, this is a nested for loop. Yes?
No, I'm really tired. I have a really dumb question.
Go ahead with the question. No question is done.
Well, no, I figured it out. I was gonna ask, like,
Ask
would
any
that only
somebody.
work if the first, well, if the ones on the diagonal were linearly independent and none of the other ones were, or else you'd like mess up your upper triangle. But I mean, you could use a different variable.
So we will actually get to that. So there is a possibility that you will discover in this process here, you move on and you get zeros. Okay? That means that actually your row 3 was a linear combination of the rows above already.
So then you couldn't solve it because you wouldn't have.
You wouldn't have a unique solution. You could solve it, but you would not get a unique solution to the system. Okay? So if in this procedure, let's say that you have your third row was in itself a linear combination of the other two rows, okay, you will actually get zeros here. Zeros are good in the sense that you don't have any contradiction. 0 is equal to 0. 0 times x1 plus 0 times x2 plus 0 times x3 is equal to 0. That is always true. The problem is when you get 0 times x1 plus 0 times x2 is equal to 7. Well, that's never true, so then you don't have a solution. Okay? So zeros, all zeros is not necessarily okay, and you would, not necessarily a problem, and you would identify this in this problem. Now, what is the second problem that I could have here? In these coefficients, look at them. What could be a problem? What if A2 tilde is a 0? Can I do the operation? So I do encounter a problem if my so-called pivoting position, this is a pivoting position, is a 0. Okay? And we will actually now solve a problem that includes that. So problems that I could encounter okay? Is that entire row is 0. So I get 0, 0, 0, 0. Okay? This means that one of the rows was a linear combination of the others. So one of the equations is simply not bringing any new information, so I don't have unique solution. Another problem, so this is first one, second one is that pivoting position and pivoting position is this. is 0. Then I actually have to switch rows. Okay. If I switch my row 2 and my row 3, does that change anything? Yeah, what do you think? In terms of a solution, does that change a solution? No. So it's really an arbitrary, our order equation of equations is really arbitrary. So actually, let's see now. Let's see now a case where we will actually need to switch positions. Okay. I have an example like that. It's called, and that is going to be called partial pivoting. So let's say that my system of equations is 2x2 plus 3x3 is equal to 6. 4x1 plus 6x2 plus 7x3 is equal to minus 6. 2x1 minus 3x2 plus 6x3 is equal to 2. So what is the system that corresponds to this curve? Zero, right? So you have actually a 0 times x1 here. So there's 0, 2, 3, 6. Yes? All right. So then my second row is then 4, 6, 7, and minus 6, correct? And the third one? And 2. Okay. So first thing, so basically my pivoting position is 0, okay? So basically switch rows. We will switch rows. So I will switch these two rows, and what I will get then is 4, 6, 7, minus 6, 0, 2, 3, 6, 2, minus 3, 6, and 2. Okay? So this is now what I work with. It's actually cool because if I want to make this into the upper triangular system, that means that I want to do all of the coefficients below the diagonal, I want to be 0. So this problem for me is already solved. With the second row, I can just proceed in attacking 2. So what will I do?
2 times negative, or negative 2 times row 3 plus row 1.
Plus row 1, okay? So let's do that. Can you do that operation? And meanwhile, I will just copy the others. Minus 2 times 2 plus 4 is 0. What's next?
12, negative 5, and
Negative
negative 10.
minus 10. All right. Okay. Now what will I do? I'm switching rows here.
You would multiply the second row by negative 6,
Mm-hmm.
and then add the third row.
Okay. So that's what I'm gonna replace here. And hold that thought. Are you writing things down? Because I'm gonna switch pages.
I'm about to.
Okay.
You're good.
Mm-hmm. Okay. So what am I going to get in this third row?
You're going to get 0, 0, negative 23,
Better be something with 23. Oh no. And I had, what did I have in the other rows, please?
2, 3, 6, 6, 7, -6.
So now I can actually be ready for back substitution because I have so-called upper triangular form. Is this 36? Can
I
we?
think it's 46.
Yeah, my notes say 46. That's helpful because I have a nicer numbers. Not that nice numbers mean anything, but it's just easier to work with them. So now I'm working with back substitution. So basically I have minus 23x3 is equal to minus 46. So my solution for x3 is 2. So can I place that now? This is my 3. This was too easy. Let's go into the second. Six and 6 cancel. So x2 is 0. And then when I do, I plug things in. So it's 4x1 plus 0 plus 7 times 2 is equal to minus 6. What is my x1?
-5.
All right. So my solution is -5, 0, and 2. I could actually place it in a vector. Can you at least test with one of the equations whether this is actually a solution? How do I test that x is correct? I'm at the test. I'm interested in getting solutions correctly because Dr. Pedanovic takes points off. So how will you actually?
You can multiply the matrix A times the vector x, and that should give you your B.
All right, and let's do that for my original. Okay, so my original was 0, 2, 3, 4, 6, 7. Oops, I'm looking at my notes. And 4, 6, 7, and 2 minus 3, 6. So if I multiply that with minus 5, 0, 2, what do you get?
Oh, you should get the same.
Yeah, did you get it?
Yeah.
I'm watching you intently, but I solved it in the meantime. So I indeed get 6 minus 6, 2. So this is basically, we verified we did the calculations correctly. And if you don't have the time or think you don't have the time, we'll test at least one of the equations, okay? So that will at least give you some consolation that the problem is correct. All right. So let's now look a little more into a problem where I have multiple solutions or possibilities for a solution. So let's look our final example for the day. Basically, we will find all solution possibilities based on parameters C and D in the following system. It's going to be a small one, 2x1 plus x2 is equal to C, and 4x1 plus dx2 is equal to 7. So I have C and D that are right now unknown, and I'm just interested in looking at what are all the possibilities for this system. We know that system could have unique solution. In this case, that means unique x1 and x2 that are solving the system. We know that geometrically that coincides with two lines intersecting at a point. I could have no solution, in which case my lines are parallel to each other. Or I could have infinitely many solutions, meaning that only one of these, basically one of these equations is a multiple of each other, so they're essentially the same in this 2x2 system. But the way I would actually attack that, I would proceed with my solution procedure, Gaussian elimination, as usual, and then analyze once I actually get to that upper triangular system. So just like before, I'm going to do 2, 1, C as my corresponding first equation of the augmented matrix, and 4, D, 7. So my next victim will tell me, what did I do here? What am I doing if I'm doing Gaussian elimination? What do I want to eliminate?
You want to change the start to 0, so you do the second row minus 2 times the first row.
So second row minus 2 times first, that works. So when I do that, what will I get?
0, D minus 2, and 7 minus 2C.
So this is where I actually start analyzing. Yeah. I don't know what C and D are, but I already hinted that if all of this, all three numbers are 0, okay, that's the case when my second equation was actually a multiple of the first one. Or if I had multiple equations, that means that my equations were linearly dependent on each other. One was a linear combination of the others. So basically, if both of these numbers are 0, this second row will just be nothing, and I will have my first equation as the only valid equation, so I have infinitely many solutions, okay? So this is where I start analyzing. So first possibility, both D minus 2 is equal to 0, which means that D is equal to 2, and 7 minus 2C is equal to 0, which means that C is 7 over 2. In this case, only one equation, linearly independent equation. So basically, I have 2x1 plus x2 is equal to 7 over 2. And the other one is just 4x1 plus 2x2 is equal to 7, which is the same thing, right? It's just multiplied by 2. So I have one line of solutions, so this is infinitely many solutions. All points on this line are solution. In practical, yes.
Why is D minus 2 0?
I didn't say why, I set it to 0. Okay? So I'm looking at I'm saying find all solution possibilities based on your D and C. And one potential, I don't know that it's a problem, but basically that I get a row of zeros here, okay? And if I have a row of zeros, then I have only one linearly independent equation. So I have infinitely many solutions. This can happen often in practical solutions, and we will actually have that example. Let's say that you're setting up a system of a traffic system, right? And you are flowing cars down the streets, and you're trying to put the stop signs and see how many cars you can actually flow through a grid in a city. Okay? So basically, flux on each street, or number of cars per street, at a given time interval is your variable that you don't know. And you're wondering how can you know, what is the extremes that you can push this system to before you grind to a halt. Okay. Is there only one solution to that system? No, there's infinitely many. I could have maybe 5 cars on Congress, or I could have 50. The moment I have 500, I'm probably in trouble. Okay? So that doesn't mean that things are unphysical. That means that simply, actually, most of the engineering problems is good when they have infinitely many solutions. Okay? Because if I have only one, then that's the one that has to be the case. And if I don't hit that one in reality, I'm in trouble. Okay? So then my system that I'm setting up, because you have to think about these systems of linear equations as something that you as an engineer are designing. So this is not necessarily a problem. This is actually, in most cases, you want to have infinitely many possibilities. So actually, when your realistic system gets into action, you actually find one of these solutions. Okay? Good. So now what's the case if actually I have one of these numbers is 0 and the other one is a non-zero? So let's say that I have d is minus 2 as a 0. So d is equal to 2. And my c is not 7 over 2, it's something else. This is the situation where I have 0 times x1 plus 0 times x2 is equal to something that is non-zero. Is that the possibility, my next victim? Intensely. So if I have d is equal to 0, d minus 2 is equal to 0. So I have 0, 0 as coefficients. And on the right-hand side, I have something non-zero. Then I don't have a solution. So this is a situation when there is no solution. And finally, if I have none of those, can I have, what's the situation if I have 7 minus 2c is a 0, but d minus 2 is not 0? Is that a problem? What's the problem?
Wait,
I don't have it.
Are you talking about like the augmented side is the right side?
So if I'm talking that augmented side has something non-zero, so basically 0, 3, 0. Is that a problem?
That's fine, because the solution is 0.
Solution is a 0. So that's not an issue. Okay. So basically then all the other cases so all other so essentially d minus 2 is not 0. Then my last equation will be 0 and this d minus 2 and I have to write it down for myself. 7 minus 2c, right? Or 2c minus 7, what was it? Can somebody tell me? 7 minus 2c. So then I actually go with back substitution. So d minus 2 times x3 is 7 minus 2c. The fact that this is non-zero means that I can divide. So this is my why x3? Because we had x3 the entire day today. Okay, 2. So this is my x2, and x1 I will get simply by plugging x2 into my first equation. So that means that 2x1 plus x2, which is this, is equal to c. So my 2x1 is c times d minus 2 minus 7 plus 2c, and I can just divide that by 2 and get x1. So in this case, I will have a unique solution, and it's going to be x1, x2. So those are all of my solutions. Questions? All right. I see you next time. We will actually look into how to form systems of linear equations.
I'm just supposed to have on the feature survey and the proposal presentation.
Didn't you?
No, I mean, it's
You had
there in
it
the
in-
write-up.
Let me stop the.
Here, and here, you know, to